minds discuss people. Average minds discuss events. And strong minds discuss ideas. A very pleasant afternoon to all the strong minds gathered here for discussing the idea of reaching Mars. I am Vishnu Rambhat and I am coming from India on behalf of my team, Indo Martian Express. My team comprises of 8 students. We are undergraduate students. We are doing engineering in Sri Venkateswara College of Engineering. Okay. We are from India. And roughly about 10 months ago, we all came together, 8 friends. We are actually 8 friends. And we looked about, we saw this competition online, and we thought maybe we could do it. And before starting my presentation, I'll just tell you how we go about it. There are 4 sections. First, there will be a set of introductory slides. Second, I will have the overview of my mission, of what we are proposing, our team. And the third, I will go into the details of each and every section, and the various sections involved in the mission. And finally, I will conclude with the advantages and uniqueness of our mission. Well, the common statement we all are aware. It's a 2-person manned Mars flyby. It should be cheap, safe, and simple. The key features of the Inspiration Mars report: it's a 501-day free written flyby. Okay. 10 months ago, when we came together and sat down, the first question we asked was, why are we doing this mission? Because in a flyby we're not landing or we're not doing anything. Of course, the ultimate aim of a flyby mission is landing and colonizing Mars. But then a flyby is very important. This is something like a prequel of landing. We are proving many technologies like the life support systems, the psychological, physiological effects for such a long duration transit on the crew, and various things. Well, in Inspiration Mars, it's a free written flyby, and there's one essential technology that it's not proving. That is propulsion system. For any landing mission, a propulsion module is very important because you have to land, take off from Mars, and come back. Whereas deep space propulsion is not been tried as of now and on a manned mission, and it's absent in a free written flyby. So we thought, because we're spending a lot of money in doing this mission, so why not go for a powered flyby, so that we'll be proving more technologies and we'll be more confident for future missions. And so these are the 3 things we'll be covering in a powered flyby. Now, the second section of my presentation, it's the overview of my mission. It's a 431-day mission, so 70 days. It's shortened by 70 days, and it's just a single launch. It's very simple. SLS Block 1, transmass injection of Delta V 3.58, 160-day long forward leg, and the flyby burn will be of 1.78 kilometers per second at the periapsis of Mars, and a 271-day return leg, and a skip re-entry method to manage the high re-entry velocities. So this is the mission infographic. On May 10th, that is, we will be launching 5 months later than the original proposed launch date. So we'll have more time for the scheduling. We'll have more time for the entire mission development, and we have C3 of 8 kilometers square per second square, which is lesser than the original Inspiration Mars report. And the forward leg will be for 160 days, and the flyby burn of 1.78 will be performed at the periapsis, the return leg, and the skip re-entry. Well, the skip re-entry velocity is very high. I'll deal with that when we come to the re-entry. Mission trajectory. For any mission, the most important part is the mission trajectory. That's the first step. We went into NASA Ames trajectory browser. This is not, it does not compute your trajectory, but what it does, it's already computed many trajectories, and it's a repository of trajectories. And we searched for our mission, and we got, we got these outputs, we got these many trajectories, and we selected this one right here, because it's got the least escape delta V, that is 3.58 kilometers per second. And we selected that trajectory, and with that, we got these parameters. The launch of the C3, characteristic energy of 8 kilometers square per second square, and the parameters are there, so on so. Earth departure will be on May 10th. On October 17th, we will perform the flyby, and that is the Mars arrival, and the return back will be on July 16th. So the entire mission is covered within 431 days. Less duration. Less duration means less exposure to radiation, and less cargo, I mean less supplies for that, and we can reduce cost and operation cost will reduce, the amount of food we are taking, everything, we can curb cost using that. And this works by Lambert's two-body solver, which means this is a primitive design. So we have to have further analysis to perfect this trajectory, and also this has been done by patched conic approximation. Because there are two different trajectories, it's combined. After the flyby burn, the eccentricity of the trajectory will be different. So, it's combined using patched conic approximation. Now, the spacecraft architecture. What models are we going to use? We are going to have Dragon, Cygnus, a propellant module, solar panels, and propellant thrusters for reaction control systems. Well, why Dragon? Dragon can, it has re-entry capabilities. Has a life support for the crew. But the space inside Dragon is not enough, so we need more space. We evaluated many designs like inflatable modules and other things, but we finally stuck on to Cygnus by Orbital Sciences Corporation because it gives us a lot of flexibility on the internal arrangement of systems, and it's a very comfortable module to use. And then comes the propellant module. We use a RL10V2 engine. It's a bipropellant, it's a cryogenic engine, which will give us the flyby burn at the periapsis of Mars. And we have 80 carbon panel and 16 thrusters used for RC control. This is the mass budget. If you see the total value sums up to 23.369 tons. So we'll have to lift this much mass to low Earth orbit and inject it towards Mars. And this is the propulsion module. This is based on Advanced Common Evolved Stage by United Launch Alliance, and RL10V2 has a specific impulse of 464 seconds. Boil-off rate has been considered as 0.05% per day, and accordingly the excess amount of fuel to be carried also has been incorporated in the design. The fuel tank will be a common bulkhead, and it will have liquid hydrogen and liquid oxygen as a fuel, that is a fuel for RL10V2. Coming to the propulsion. Now we know what is a trajectory and what is a spacecraft module and what is the weight of a payload. So we have to lift 23.36 tons to low Earth orbit and inject it. Which launch vehicle can we use? To maintain mission simplicity and avoid on-orbit rendezvous, because as such this mission is a very long duration mission, we have enough risks, and we don't want to increase the risks by having on-orbit rendezvous and other operations. So we wanted a single launch. Of course, even Apollo mission was a single launch. So there shouldn't be a problem with that, and payload 23 tons. And this is the performance of SLS Block 1. And this should be ready by the end of 2017. And our mission is in the mid-2018. So we should have enough time for incorporating our systems in this and using SLS Block 1. For our characteristic energy of 8, we get a payload of 23,500 kilograms, so which is well within, so we can carry our payload in SLS Block 1 comfortably. So we've gone for this. And also, the cost of SLS per launch, one launch will cost $500 million. It's quite expensive. So we wanted to try other economical alternatives like Falcon Heavy by SpaceX and all that. And from this we see for the required delta V, that is 3.58, we get only 14.3 tons. So which means, it places a constraint on the mass budget, and so we stick on to SLS Block 1. It's fine with us. Radiation shielding. Two crew will be subjected to a long duration galactic cosmic radiation in outer space, and this can cause cancer risks and various health hazards. So this is a very important aspect to be addressed. And according to PEIR standards, 600 millisieverts is the limit, above which to cross the 1% chance of developing fatal cancer. And compound shielding has been adopted for attenuating the GCR dosage to safer limits. And from this graph, as you see, liquid hydrogen and water gives good attenuation, but we've stuck on to polyethylene for benefits like less mass, and it's easy to incorporate and doesn't need any extra power and things like that. And so what we've done is we've considered the Cygnus module as we've modeled it as a hollow cylinder, and we have calculated the aerial density. air density comes up to 5.284 grams per centimeter square. And for that density, from the graph, we can calculate how much of attenuation it costs and how much radiation enter the spacecraft. It comes up to 634 millisieverts per year. This needs to be reduced. So what we do, we do compound sheeting using polyethylene. Using the same graph, we calculate the thickness, that is Beer-Lambert's law of attenuation of radiation. Using that, we calculate how much is the thickness required of polythene to attenuate it and bring it down to 600 millisieverts for 431 days. We reach 508 millisieverts per year and we extrapolate it for 431 days and it comes up to 600 millisieverts. And thus we bring the cancer risk down below 1% chance of fatal cancer. And the additional mass because of this incorporated is 513 kilograms. This has been added to the mass budget. Then comes attitude control. And attitude control is very important for a long duration mission because now and then the course correction has to be incorporated so that we travel in the correct path and reach destination. And as such, we have various systems incorporated in Dragon, Cygnus, and the propellant module itself. For example, the propellant module has IVF technology, integrated vehicular fluids. This is a primitive technology, so, and these are, all the other technologies are proven technologies, like they have GPS. GPS works, of course, within the Earth atmosphere, like for during re-entry and during launch. And the other IMU and Star Tracker units will function from Dragon and Cygnus. Apart from this, for thrusters, we have incorporated 16 bipropellant thrusters, in clusters of 4, by Northrop Grumman, that is CRT-1 to 100. These are the fuel, and we have estimated the course correction required for this duration of a mission, and it comes up to this much of del V. And when you come to the value, how much of fuel will be required, and we have that much of that. And Dragon spacecraft is also providing with 1,300 kg of propellant, which are reserved only for the re-entry. That will not be used for any course correction in normal operation. Then comes environmental control, the life support system. Well, this will have 5 sections: air, water, food, waste, and human accommodation. Talking about the air management system, this is used in ISS already. We have potable water, oxygen generation system. We'll split it to H2 and O2. O2 will be fed to the crew cabin. Nitrogen is also necessary because in normal atmosphere we have 70% nitrogen. So that also be included, but won't be absorbed by a human. We won't consume it. So it will just remain. Only for the leakage, we have the nitrogen storage. We'll keep adding it for how much of it is leaked out. And we give out carbon dioxide. The crew will give out carbon dioxide. That will be absorbed by 4-bit molecular sieve. And that then it will be fed to sebaceous equipment at higher temperature to react with hydrogen produced at OGS, and it will give out CH4 and H2O vent. CH4 vent and H2O to be fed back to the potable water system. Whereas in the OGS system, the amount of hydrogen produced is not enough, so we have a hydrogen storage tank also for that. And the amount of CO2 produced for two crew members for 1 day is so and so, and for 2 is consumed is 1.6 kilograms. And this is the system sizing. How much will be sufficient for the entire mission, and subsystem mass comes up to 759 kilograms. Potable water tank is common for water management and air management system. For water management, these are the base values: how much you consume, how much you are giving out, and everything. And the group body wash and flush, how much will be required. And this is the technology we'll be using for for our purification of water. The amount of water we'll be carrying is 275 kilograms. But for 431 days, the amount of water necessary will be around 300 kilograms. How are we going to meet it out? We're going to recycle it. But we cannot reclaim all the wastewater back into pure water. Only 98% can be reclaimed. So the 2% will go, we'll be losing 2%. And when you calculate, on the end of 431 days, there won't be any water left. All the water will be in waste storage tank. So which means we have used up all the water. So we're taking exactly what's necessary for the mission. And this is the water purification system. And the food management system, how much of food will be necessary is 531 kilograms for 2 crew members for 431 days. The volume occupied is 14.95. Power requirement for the storage is 1986.78 watts. Waste management system, these are the base values. The volume occupied by the waste management system, power requirement, it's all given there. And the solid waste collection and the solid waste treatment. Human accommodation. We have the various items and how much mass each one has. But for clothing, we have reduced it. say like they can use, they don't sweat much or anything in outer space, so maybe they can use a particular clothing for two days, and we have sized it down for 288 days. And other things, yeah, how much of it is necessary, we've given it, and the total comes up to 1,185 kilograms. This includes portable life support, medical supplies, recreational items, and X-rays equipment also. Power systems. Well, power is very essential in outer space because that runs all the other systems. Yeah. Power requirement for each module has been tabulated. The total requirement comes around 10,000 watts, 10,786 watts. How are we going to meet it out? We are going to have 80K reflex panels. In this graph, we can see how much power is required and the diameter of the solar panel. And from this, we'll have a pair of 3 diameter sized solar panels on Cygnus, 4.8 diameter on Dragon, which will produce that much of power, and that will be sufficient for running the spacecraft. Telecommunication. In telecommunication, the amount of, we have based a telecommunication system based on MRO, or Mass Reconnaissance Orbiter. These are the values which will be necessary. For video conference, if you notice, it's very low. That is, we have kept it to the minimum. That is, we can do a video conferencing, but it won't be of high definition or anything, because to reduce operation cost. The total comes around 160 kbps, and we are using for this we are using deep space network and expand communication. Yeah. So that's the telecommunication. Coming to crew factors. Crew selection, okay. The crew members should be a married couple, and the average age should be 40 years, because only 40 years we are trading off between the muscular and the skeletal strength and the resistance to radiation. So average 40 years of age of crew will be apt for this mission, and the crew members should be non-smoking, of course. The crew members should be free from psychiatric disorders because it's a long duration mission within a small capsule. And one member of the crew should be an engineer to, to check on the ECLSS systems and other systems. Whereas another crew should be a physician. We are carrying a lot of medical equipment also, so we are not taking that for nothing. So a physician, he should be able to go from onward surgeries. And we have devised a crew activity schedule for them. And the amount of energy involved in this, if you see, it sums up to 11.85 megajoules per day. And this is very close to the standard metabolic requirement, which is 7.82 megajoules per day. So which means they won't be overflowing with energy, or at the same time they won't be, very tired. They won't strain themselves, and they won't become tired. Risk analysis. This mission is very risky, of course. It's a long duration mission, so it's very important to analyze this. For this, we have taken all the major risks and given it alphabets. There are 2 slides of thing, and we have put it into this matrix. Whereas here is the possibility, the likeliness of happening, and there is severity. If you notice, we have brought on most of the risk within the moderate region. Nothing lies in the red, but still the F, M, E, these are very severe. So those shouldn't happen. So we should take enough measures to avoid them, like during flyby maneuver inaccuracies. Sorry. Yeah, the skip re-entry inaccuracies. That is because we have a very small margin while entering, and the failure of the thermal production system. And finally, we have another very important, the propellant module failure. Because this is a powered flyby, the propellant module should function properly at the peri-axis. Else they will land somewhere else, because they have to come back here. That's very important. So these are the risks, and we've analyzed that, and we hope we have all the risks under control in our mission. Coming to re-entry, yeah. Re-entry, yeah. According to our trajectory, we'll be entering the Earth's atmosphere at 15.66 kilometers per second. This is very high. If we perform this will be a record-breaking re-entry speed. We have never tried this speed before. And the main requirement will be we have to reduce the G loads. Because the crew members are exposed to microgravity for such a long time, their bone density will be very low. So they cannot, bear high, heavy G loads. So we have to bring them down. And also the heat flux. We have to manage this heat flux. A lot of heat will be generated. And the physical parameters of the re-entry is given. And the angle with which they should enter is 6.25 degrees and 6.35 degrees, so that the G load is, that's taken from this graph. And the velocity reduction after the skip is observed to be 42.5%. The second re-entry will be elastic, of course, the dual parachutes, the main parachutes, and okay, iridium beacons. And it's a regular procedure. Finally, the crew will be brought back to Johnson Space Center for their rehabilitation. Cost estimation, yes. For per launch is 500 million. The other modules have been totaled down. It's 720 million. These are the mission subsystems. The various cost estimate has been brought down. I mean, we have summed up to 549 million. And the operation cost, this is based on DAS and aperture cost tools, and it comes up to 49 million. And the total cost, that is 1.31 billion US dollars. The total cost comes up 1.3 billion dollars. Scheduling. The scheduling we have based mainly on the Inspiration Mars design schedule itself. And if you notice, we have a little extended period. We have another 5 months time in the end because launch is on May 10th. And yeah, we are already there. We should have started by now, I guess. 2014. It's high time we hurry up and start the mission. So, of course, in Apollo 8 lunar mission also they face constraints in the timing, and but they did achieve it. Yeah, so it should be possible by 2018. And then the conclusion. Well, the unique advantages of this mission. Why go for this mission? Duration has been reduced, which means reduced radiation hazards. Number 2, less cargo is required. Number 3, psychological effects and physiological effects will be lesser because the duration is lesser by 70 days. Okay, mission abort system, we are in the forward leg. We have a propulsion module right behind us in the spacecraft. So in case anything goes wrong in the first 160 days, we can fire the, we can orient the spacecraft in a particular angle, we can fire the engine we have, and we can come back to Earth using a proper when you do the proper analysis for the first 160 days. So it increases the redundancy of the mission. And finally, we are proving the deep space propulsion system, which will be very essential for future missions to come, that is landing and colonizing, etc. These are the references. I hope you don't want to
So your trajectory has a number of advantages, but it also has this disadvantage of the very high re-entry velocity at 15.6 kilometers per second. You discussed it a little bit, but could you discuss a little more on how you're going to deal with that problem? Because that seems to be the tall hole in your plan for you.
Yes. Okay. For re-entry, we are using a skip re-entry method. And when entering at a shallow angle of 6.25 degrees and 6.35 degrees, the G-loads are minimum, and at that shallow angle, the spacecraft, that is Dragon alone, only will re-enter, of course. We will be leaving out the propulsion module and the Cygnus in outer space. When the Dragon re-enters, it tends to skip. And because of the skip, when you go outside, we will be giving out, there will be a lot of heat generated because of the shallow angle. When you go out, the heat generated will be dissipated in outer space. And then we re-enter at the lower velocity, that will come to 42.5% in sense, come around 8 to 9 kilometers per second, and that can be ballistic.
I think you lost one of your axes in this plot. Do you know what the G load is actually?
Yes, sir. The y-axis is the G load actually. It's not visible.
What is it?
Oh, on the right side.
Right side?
The G units. Where are the G units? G load.
Top right text.
Yeah, so it's the bottom of that tree and top over the top left.
Yeah, these are the velocities actually for the velocity during skip. And for the G-loads, I think I'm missing the units there.
But are you able, you'll have, in order for it to re-enter again after the skip, you're going to have to lose about 5 kilometers a second velocity on your first traverse through the atmosphere. And you've calculated that you can do that?
Yes, so we've been trying to model it, but no, we didn't get accurate results on that, so I'm not putting it up on the slides here. But on further analysis, it will be possible because we were getting close enough results. So by Yeah, in case we're not able to accommodate such speeds, we can, modify the thermal protection system and the heat shield in a particular angle, and it should be possible because at that speed we should be able to manage such speeds. Yes.
Other questions?
Just a quick one. Can you describe how you calculated that your propulsion module had the capability to do this, to do the delta V you needed? It seems small to me for that one stage.
The propulsion module, we have about 8.5 tons of fuel, and leaving off the boil-off, there will be around 800 kilograms of fuel being gone for the boil-off, and we calculated based on the performance of the R10B2 engine for performing that for del V, how much of fuel will be necessary. We calculated accordingly, and we added the necessary the accounting for the boil-off also, and we sized the common bulkhead tank for that.
Did you look at, with this alternate trajectory design, how sensitive that would be to different launch dates?
So actually, these were the most comfortable launch days, and we stuck on this. Yeah.
And I guess you made this decision to add that burn as being required. Did you also look at how that would compare to basically putting that delta V into the mission right at the very beginning and then going on a longer transfer?
You mean reducing the duration further?
So basically, I think you're decreasing the duration by doing a burn at Mars. Did you think about the risk of that burn versus the risk of just having a longer mission?
Yes, of course. Carrying an engine and proper, the fuels and everything for that long duration in outer space is a risk, first of all. And second thing, having an engine idle for 160 days and then firing it back after 160 days should work fine, because in case it's not working, that's another risk, of course. But maybe we can, in outer space, we can test these engines for such durations and things like that, and we can reduce the risks of that, because we can do some testing before that and make this thing happen.
Is there any margin or reserve in your cost estimate? The 1.3 billion?
I'm not really sure of the margins, but
No, is that 1.3 just the numbers you got by adding it up? Did you put any extra 10, 20, 30% on that?
no, sir, we didn't give any margin for that. We just added up the cost that we got on different modules.
If you had the chance, would you fly this mission?
Yes, I think I would fly. Because not everybody gets to go for a flight to Mars. And I'd be the first human being to go to Mars and come back, so I'll definitely go for it, considering the risks.
Point of clarification, Scott. The relevant factor for judging cost for these missions is not their estimate of their cost, but your estimate of their cost.
I understand that we should, maybe we'll discuss this when we have our group session about cost risk versus, that sort of thing. Not just curious.
Okay, thank you very much.